Hi guys, I'm Hedgeberg. Welcome to what is currently named Hedgeberg Teaches Electronics and will probably change soon when I think of something cleverer. It's just midnight 30, 12:30. Yeah, sorry, I'm dying a little bit. I've been extremely busy. It's part of the reason I haven't been working on the boot ROM work. So in the meantime, I thought I'd actually record this. I proposed the idea of doing a mini lecture series on fundamental electronics, and it was received really positively. So I'm going to go ahead and record this first episode. Today we're going to go ahead and review, and I'm going to go ahead and try to teach the basic necessities for understanding analog circuits. So there's a few pieces to that. The first of which is Ohm's law. There's also Kirchoff's current and voltage laws. And after that, I'm going to go ahead and provide a basic example problem of what this enables you to do. But before we can get into any of that, I want to go ahead and quickly touch on what any of this means. One of the things that a lot of when I teach students in so some background, I teach a course in analog electronics at Carnegie Mellon University, depending on the semester. And one of the things that I find students fail to understand a lot of the times is what's actually happening in circuits. So it's my opinion that before any of this begins, students should try to understand what exactly is happening. So the first thing that you need to understand is what a circuit is and does. So I don't want to get too into the physics of circuits in general right now, but I do want to give enough of an overview that you can understand why they behave the way that they do and what's happening. So the first thing that you need to understand is in circuits, there's two things that really govern why things are happening the way that they are, and that's voltage and current. Those are both derived from physical values that are simplified in order to make analyzing circuits a lot easier. But when we talk about circuits in general, a circuit is always a simplification, really. What's actually happening is, let's say that we have an electric field, and you don't need to know heavily what that is, but the best way to think of it is, let's say that there's some big positive charge. We could call it a really big proton, something like that. At some point, I'll go ahead and give a better, more in-depth explanation of what all of these things mean. But let's say that we have this big positive charge. This means that there's a positive electric field. These arrows are backwards, actually. What am I doing? I'm sorry. I'm very tired. There's going to be some mistakes in this. I'll probably re-record it at some point when I'm less tired and have more of an idea of what the teaching style for this will be. But let's say that we've got a large positive charge here. This positive charge is going to radiate out a pull. This is where the phrase opposites attract comes from. Positive charges attract negative charges and vice versa. In reality, there are two things that form these charges. For the purpose of this introduction, two kinds of matter, protons and electrons. Protons and electrons are really the only two sources of charge. So protons have a positive charge and electrons have a negative charge, and they attract each other. There's a lot of things that happen at the quantum level that prevent them from, in general, contacting each other inside of something like an atom, but so when you get to atomic physics, a lot of this gets very strange. But if we're just talking about something like a proton and an electron, you can think of a proton as emitting a positive electric field, and this causes electrons to move towards it. It exerts a force on the electrons, and vice versa. They also exert a force on protons. So let's make up an imaginary situation that would never happen, which is that this is a very, very strong, magically powerful proton. It's very, very positively charged. And you've got metal, something like a bar of metal. Now, electrons, if there are electrons clustered over here at the end, which usually in something like a conductor, if a conductor had a charge, the electrons would be equally distributed across the surface of the conductor. In this case, we're making some magic assumptions, but you have these free electrons that are here. They're going to move, and they're going to move until the forces are balanced. But in the case where you can go ahead and make a positive charge and you can supply, and the positive charge can become basically a sink for electrons, and you have a negative point which can supply electrons. And so we can think of these as being infinite, which, again, all of this is a model to make things a little bit nicer. A lot of this is inaccurate, and I wish I could go more in depth on this, but that is far beyond what I have the energy to do right now because I am about to go to sleep. I have an all-nighter to pull tomorrow. So, yeah, this is going to be probably relatively useless in a lot of ways, but I hope somebody finds it useful. If one person finds it useful, I'm happy. Basically, electrons will flow from the negative source where there's a supposedly magical infinite amount, and they'll go to this positive source, which we can treat as a black hole for electrons. In reality, they'd actually continue to flow like this across that, but right now, you can think of it like this. So all of a sudden, we have this current of electrons because of the fact that there is a potential difference. There's a negatively charged source here and a positively charged source here, and electrons want to go towards where there will be charge neutrality. i.e., they want to make they quote want to make the charge zero. This is something that's really important to how circuits work. The idea that charge moves in a direction because of electric fields. So you have current, which is electrons which are flowing through this circuit element, which I'll call this L for load, meaning it could be anything. So you have current moving through the circuit because of the fact that there is a voltage difference or a voltage source, which looks like this. And now I'm going to do something which is going to make this a little bit counterintuitive, and I'm really sorry. But when we started to understand how circuits worked, it was long before we understood what an electron was. So we had a misunderstanding about how charges move through circuits. We had this idea of what positive was and what negative was. So we assumed that in the same way that a hill works, where something rolls from high to low, like a ball, because of gravity and the gravitational force, we assumed that things must be moving from positive to negative. Now, both of those are fundamentally abstract. You might be thinking to yourself, why did we decide what we did? The answer is because. And so we had this idea for how circuits were behaving long before we knew what was actually happening in them. We knew current existed, but we didn't know why. So we did the awful, awful thing of saying that current is opposite to the flow of electrons. And when we discovered how things actually were, sorry about that, we discovered how things actually were, we refused to change it. So nowadays we have the horribly counterintuitive idea that current moves opposite to the flow of electrons. So a voltage in a circuit induces a current in the other direction. That's basically all that you need to know about this, but it gives you some idea. Now, in a perfect world, if you have a wire, so if you just had something like this, all of the current, all of the electrons would just flow, and so you would have infinite current coming through this, and this source would just keep on trying to correct the imbalance. In the real world, however, wires that behave like this don't exist. The reality is that there's matter in the way. If you try to throw a ball at a wall, it's not going to go through the wall unless you're very, very strong. If you tried shooting a lot of I don't know how I'm going to make this analogy. If you try throwing a lot of very, very small balls at a wall with a lot of holes in it, a lot of the balls will go through, but some of them won't. A wire is like this. It's like the wall full of holes. A lot of the balls will go through it, but some might get bounced back and have to be thrown again if you want to get them all through. This idea of a wall is representative of how electrons behave when they're moving through something. You have something that's called a resistor. And a lot of you have probably heard this term but not understood what it meant or had some general intuitive idea of what it meant. But this is why. Electrons are, in effect, there's something that impedes their flow. So a resistor is the first form of what's called an impedance in a circuit. So instead of all of the current being able to flow through, there's something limiting it. A lot of times you hear of a model of pipes when talking about circuits. The idea that, for example, if you had a pipe that looked like this, that's not right, and you were pushing water in, you've got one level of water pressure here in this section. You've got a different amount of water pressure in this section because of the fact that the water constrained now exerts more force on a smaller surface area. If you think about it from that perspective, then the smaller the pipe you make, the higher the resistance you're going to have. Or the longer you make it, the more resistance you're going to have. And so the more current you're going to prevent from flowing through that. There will still be current through it. It just eventually, when a circuit reaches equilibrium, there's a certain amount of restriction going through there. So we have Ohm's law, which is a really fundamental part of analyzing any circuit. And the version that we're going to talk about right now, and this is not the only version of Ohm's law, but it is what we're going to use for most of this until we get into slightly more advanced situations, is V equals IR. What this means is that voltage is current times resistance. So let's say that we have a plus or minus 5 volt voltage source and a 5 ohm resistor. Then we know that there's current coming through here. V equals IR. If I said I wanted to figure out the current, I would say I equals V over R, which is equal to 5 volts over 5 ohms, which is equal to 1 amp. So that is the very simple version of Ohm's law. So now we need to go ahead and quickly discuss Kirchoff's current and voltage laws before we can get into starting to analyze some circuits. So you now have, and Kirchoff pointed out that circuits have to behave conservation of energy. So for example, all power into a circuit needs to leave the circuit. You aren't, in a circuit, if you're pushing current in, you're not going to end up with electrons that stop moving. There's still a force on that electron. And even if it gets stuck for a while, it's still going to keep on moving. So in general, because of the fact that all power in has to equal all power out, you have Kirchhoff's current law, abbreviated KCL, and you have Kirchhoff's voltage law, abbreviated KVL. I should move this a little bit. Kirchhoff's current law dictates that if I have a bunch of nodes, like so, attached, then all of the current that comes in has to be equal to the current out. So we can call this IN, and then we've got I1, I2, and I3. Then IN minus I1 minus I2 minus I3 needs to be equal to 0 to obey the fundamental theory of energy conservation. This can also be written as IN equals I1 plus I2 plus I3. You also have Kirchhoff's voltage law, which states that in a loop, something like this, voltages must sum to 0. This one's a little bit more complicated and a little bit less intuitive, but it works like this. If you choose a point inside of something that looks like a loop like this, you can say that on one hand, there's something there, and on one hand, the voltage source is going to be creating a positive field on this side, a negative field on this is going to create a positive field here, and a negative field here. These I'm sorry, that's a little counterintuitive. There's a better way to think of this. The voltage source is inserting power. What this means is that this power has to go somewhere. The power is not just going to be cycling endlessly. So for all power that's inserted, it has to be dissipated. Resistors don't add power. You can't turn on a light bulb by hooking it up to a resistor. It needs to be hooked up to something like a battery. A battery is quintessentially a voltage source. So when you have something that's inserting power, you also have elements that are dissipating power. So these also have plus minuses. So some people say that you should organize your circuit like this and then just do everything top down. That's one way to look at it, but the better way to think of it is, you know, current is moving through this circuit like so. If something's dissipating power, then its plus and minus are opposed to the flow. Whereas if something's inserting power, its plus and minus are in line with the flow. So see like this. So this voltage source here, sorry about that. This voltage source in green, encircled in green, is adding power. These two are dissipating power. And so that's how we can think of we can think of current in relation to voltage when we think about power dissipation or insertion. So because this source is generating power, it is the positive node is where current is coming out, whereas for these resistors, the power is moving into the positive node. So you actually have voltages. So you have Vn, And then these resistors have generated a voltage of their own because of the fact that power is being dissipated. So the voltage at the top and the voltage at the bottom are not the same. So you have V1 and V2. And there's one other thing that I should point out is that this is grounded. What a ground is it's a reference point. All voltages are relative. So when we see a ground, we usually assume that V at ground is equal to 0. That doesn't mean that there's an absolute 0 volts, because that's not how electronics work. Voltage is something which we look at and we know it exists as a difference in the strength of an electric field between 2 points. So the electric field here is stronger than the electric field here, is stronger than the electric field here. Outside the circuit, there might be another spot where the electric field is even lower, in which case we could say that it would be less than V ground. But for the purpose of this circuit, and in general when you work on things, things are mostly going to be positive. That's not always the case, but when things are negative, all it means is that they're lower than ground. We could say, if we wanted to, that ground could instead be 5 volts. And all that would mean is that you shift everything up 5 volts. And it's still true. Ground doesn't need to be 0 volts. It's just more of a standard for making these problems easier. So all this means is that if you make this loop following the direction of the current, then you can say that all of the things that are inserting power, so all sources basically, are equal to all the things that are dissipating power, so V1 plus V2. So in the end, the net voltage is also 0. So current into a node is equal to current out of a node. Voltage in a circuit is equal to the summed voltage of the consuming elements. It's a relatively simple thought, but it has a lot of implications in how we treat circuits. So let's go ahead and start working on this. The first thing that I'm going to do, I gave you one example of a simple 1 resistor element, and that's just Ohm's law. Now let's go ahead and do 2 resistors. When you deal with 2 resistors, it's relatively simple. There are 2 resistors in this kind of configuration. This is what's called a series resistance. Series resistance just means that all current through one resistor will be equal to the current through the next resistor. In the case where this happens, this means that I R1 equals I R2 because of Kirchoff's current law. So all of the current into this node is equal to all of the current out of the node. So because IR1 is equal to IR2, one second, a little bit of a brain fart. Because IR1 is equal to IR2, and the current is traveling through it, the simple explanation, and I'm not going to go into the derivation because it's not terribly interesting, is just that resistors in series can be summed. So if we wanted to solve for I in the end, all we would have to do is make an equivalent resistance that we'll call REQ. What was that in the background? If you guys heard that, do some interesting analysis and tell me what it is. I hope I'm not going to die. Just sounded like a spring or something. But I don't know. I'm tired. I'm sorry. So we have current through here. And so all REQ is equal to R1 plus R2. So if R1 is equal to 1 ohm and R2 is equal to 2 ohms, then I is equal to Vn over R1 plus R2 is equal to Vn over 3 ohms. So that's a series configuration. There's one other kind of configuration of resistors that you need to know about, which is parallel resistors. What that means is that you have something like this. So we're going to have Vn R1, R2. So because we have Vn, then you know that there's a voltage across both of these. So both of these have current going through them. And the voltage across these is the same because they're both hooked up to the voltage source. So we have I1 is equal to Vn over R1 and I2 is equal to Vn over R2. So the total current, I total, is equal to Vn times 1 over R1 plus 1 over R2. Now this is what's cool. If I go ahead and do I total, if I divide both sides by Vn, I wind up with I total, I was going to do this, divide by Vn, meaning these cancel out, and I get I total over Vn, which if you remember Ohm's law, V equals IR. And if you divide both sides by V, and then you divide both sides by R, you get I over V is equal to 1 over R. So we can say that there is an equivalent resistance, that this is 1 over Req, which is equal to 1 over R1 plus 1 over, where did that go? Sorry, so you guys can't see it on screen, but there's a little box that I'm writing in because of the fact that if I were to try, where my hand isn't detected, because if I were to try to just write on my iPad screen, this would be a garbled mess of scribbles. Not that it isn't already, I have bad handwriting, but it's better than it would be. So this is how parallel resistors work. And if I were to go ahead and extend this chain up here into infinity, then I could extend this into infinity as well. So I would do plus 1 over R3 plus ... up to 1 over Rn. What you need to know, though, for any of these problems that I'm going to be giving you, is just how to do two elements in parallel. Because if you want to, you can just simplify things down in a chain. So if you had 3 resistors, you could just combine these two using what I'm about to show you to get 2 resistors, and then you can do 2 resistors in parallel into 1 resistor in parallel. So the trick is that 1 over Req is equal to 1 over R1 plus 1 over R2. And so if I go ahead and say, first of all, I need to combine this side. So I want to multiply top and bottom of this fraction by R2. And I want to do this one by R1 so I can get the same denominator. So I can add them. So I get 1 over Req equals R2 plus R1 over R2 times R1. So because of the fact that it's the inverse of Req, we get Req is equal to R2 times R1 over R2 plus R1. And so from now on, I'm going to abbreviate this format as R1 parallel R2 to make life a little bit easier for everyone, because most of when I do these equations, I'm not going to be plugging in values usually. And so simpler notation is better. So all of this goes ahead and gets us to a point where we can start solving much more challenging resistor grids. So let's say, for example, we have a voltage source. And I'm going to go ahead and draw 2 resistors here. I'm going to go ahead and assign a ground here to make math a little bit easier going forward. So here's our simple resistor grid, but it's more complicated than anything you guys have dealt with. And so this is R1, R2, R3, R4, and R5. Here's Vn. And there's a few things that I want to solve for here. I'm going to say that we want to solve for I sub t, the total current. I want to solve for VA, and I want to solve for VB. Okay, so here's how we're going to go ahead and do this. First thing is that we want to go ahead and make this circuit simpler. So we want to figure out, first off, to figure out how things are behaving inside of the circuit, we need to get some kind of foothold in the circuit. To get a foothold in the circuit, usually it's best to go ahead and figure out how to make things simpler. When you have a big string of resistors like this, usually it's best to think of how you can collapse them using the tricks that I just showed you. So what I'm going to do is I'm going to go ahead and take R1 and R2. Let me choose red here. Because so these two, and because they're parallel, I can combine them into a single Req, substituting for 1 and 2. I can do the same with 4 and 5. Okay, so let's go ahead and get to our first circuit. So we're going to go ahead and say R1 is parallel R2. So we have, let me go ahead and just, my mouth is running faster than my hand is, so just slow that down. Here we go. We've now gone ahead and taken these parallel resistors and combined them into equivalent resistors. So we now have Req 1, 2, R3, and Req 4, 5. Oh, and because somebody was wondering what Req meant, if it didn't make sense earlier, that just means equivalent resistance. So Req 1 and 2 is the equivalent resistor formed by substituting out resistors 1 and 2 for a single resistor. So this is equal to R1 parallel R2, and this is equal to R4 parallel R5. And now I can actually add all of these together to get to one resistor. Plus minus V in. And I'm going to say that this is Req T for total resistance. So this is the equivalent total resistance, which is equal to R1 parallel R2 plus R3 plus R4 parallel R5. So now I have my total current, and I can solve because I should have that lowercase, sorry. So we have our input voltage, we have an equivalent resistance, we can solve for the current. So I total is equal to V in over R1 parallel R2 plus R3 plus R4 parallel R5. Yeah. Now we can go ahead and say that now that we've solved for IT, check mark, we never need to go ahead and look at this nasty looking fraction again. Instead, we can go ahead and look at how to get the rest of the other two values that we need, VA and VB. So I'm going to go ahead and copy this intermediate circuit that we drew because this is useful. So this first round was just using resistor collapses and Ohm's law to get the current. This next part's a little bit trickier. We know that we have VA and VB, and these are in reference to ground. So how do we solve for these? Well, we just calculated the current. Since we've just calculated the current, we know that this current, by Kirchoff's current law, is going to be going through all of these resistors. Because as the current leaves the resistor, it has to enter the next one. So the current through this equivalent, the current through our first equivalent resistor, our R3, and our final equivalent resistor is all the same. So we know that VB, so the way that we're going to do this now is we have Vn is equal to VREQ high plus, and that's just what I'm naming REQ 1 and 2, just so I don't have to deal with subscripting parentheses, because that would get really messy, and I don't think anybody would like that, plus VREQ low. So all that means is that each resistor has a voltage across it. Now I can say that VB, because of the fact that the voltage below this resistor is 0, let me go ahead and circle it in red pen. We know that the voltage, because of the fact that there's ground here, we can add a VC, which is effectively 0. So what we're really asking is, or what we're really going to say here is VB minus 0 is equal to, so VB minus VC, which is equal to VB minus 0, which is equal to VB, because of the fact that all voltages are relative, like I said, to ground. So VB minus VC is equal to VB minus 0, which is equal to VB, which is equal to, I'm sorry, my B looks like an S. That's horrible. I need to work on that. Subscribe to me on Patreon, and I'll get better at handwriting? I don't know. I'm sorry. This should be really serious, and I'm making jokes instead. One day when I renew this, I will be less silly. So we know the current through this resistance, which is I total, and we know that this resistance is R4 parallel R5. So now we've solved for VB. And how do we get VA? Well, we do the same thing. We know VB now relative to ground, and we can get VA relative to VB via VA minus VB is equal to I total times R3. So VA is equal to IT times R3 plus VB. And that's how you get all of our values. We have VA, we have VB. I'm gonna fix that because that's, oh geez, that's awful to read, bad to look at. Okay, so we have VA, we have VB, and we have IT. Just like that, we've gone ahead and solved for all of the unknowns in this circuit. And so with that, that's basically all you need to know about resistive arrays. This is the basic idea that you go through when solving a circuit. And it's going to be the same for basically every circuit. You'll be changing out elements because not everything is resistors. It's far more complicated than that. But this is the basic thing that you need to go ahead and figure out how to simplify and start learning how to analyze circuits. So I'm going to go ahead and leave you with a problem, which is going to look a little bit like our last one. And remember what I said about doing parallel resistors of more than 3. So there's some tricks here to make your life a little bit easier. And since this is the first episode, I'll walk you through them. The first of which is, I gave you V, so let me go ahead and give all of our values. We've got IT, we have R1, R2, and R3, R4, and R5. You're going to solve for the same thing. No, you're not. I want to go ahead and give you guys a thought exercise. We also have VA. There are 2 things that I want you guys to figure out with this. First of all, how do you do R1 parallel R2 parallel R3? What I'm going to say is parallels as an operation are associative. Look up the associative property. Remember what that is. It'll make life a lot easier. So that way you can combine these, and you can do that in whatever order you like. Just look up what I mean and look back at what I said about doing resistor chains in parallel of more than 3. The other thing is, I want you guys to try to solve for VA without solving for VB. I only want you guys to get IT and VA. Don't solve for VB. And there are a couple of ways that you could do that. Oh, I almost forgot ground here. The first of which is thinking about what the voltage is here. It should be pretty obvious, but just think about that, because we did things going up the chain. So we went from ground. Let me add some red here. It went from ground to VB to VA. What's to say you can't go the other direction? So with that, you guys have all the tools that you need to go ahead and solve for the total current through this circuit. Nope. VA. And what I'm going to do is I'm going to post the solutions at a later date because I'm exhausted and I need to sleep. But this should give you what you need to get through everything. Yeah. I really like doing this, actually. I really like teaching people. So I even though I'm exhausted, I still had fun walking through all of this. I am sure that going forward, I will do this at a point when I'm less tired. I just felt like there was an urgent need because of some questions that people were asking me. Next time, I need to figure out what exactly would be good to discuss. But I think the best thing for us to discuss is going to be capacitors and inductors and what those are and what they do. For that, you're probably going to want to brush up on some basic calculus, and I will show you some black magic that you can do with calculus to start off that section of this. And so what we'll talk about is capacitors, inductors, and how they behave in what's called the time domain. And that's going to be fun. Yeah, I think that's everything for now, guys. If you have any questions and you aren't finding this via my postings in either my Twitter, on either Twitter, IRC, or Reswitched, then, or if this is your first time even ever hearing of me, my name is Hedgeberg. No, that's not my real name. I do hardware and software reverse engineering work, mostly focused around hardware. I'm an electrical engineering graduate, and I like to help people figure this kind of stuff out. I'd like to make this into a video series. I'm sure it's going to get better and better over time. So if you're frustrated by the quality of this video, or if you're a student learning and you feel like there's something that I did wrong, please let me know what I can do to improve it going forward. Yeah, I think that's everything. Oh, right, that's what I was going to say. If you have any questions about any of this, so questions, comments, concerns, you can, of course, leave a review in the comments section on YouTube, or if you want to speak with me face-to-face, in the digital sense, I guess, you can find me on the IRC channel Keiki, on the Freenode IRC servers as Hedgeberg, or you can find me in the Reswitched Discord channel as Hedgeberg, or you can find me as @Hedgeberg on Twitter. Any of those, feel free to try and reach out to me, and I will try to answer any questions that you have. I think that's everything for now, so I'm going to go ahead and fall asleep immediately and sleep for 1,000 years. Thank you guys so much for watching, and I will see you in 1,000 years and a day after I wake up. Bye-bye.